Hello and welcome to the Theory of Computation lectures. In our last class, we learned how to convert an NFA to its equivalent DFA. In this class, let's practice some problems on NFA to DFA conversion. Okay. So again, let me start by asking you this question. What language does the following NFA accept? So this is an NFA. Can you tell me what kind of language this NFA accepts? Once again, if you have gone through the earlier lecture videos, it should be pretty easy for you to understand that this NFA accepts all those strings which start with 0, 1, and after that whatever comes we don't really care about them. So basically this NFA accepts all string over input alphabet 0, 1 starting with 0, 1. Okay, now let's try to convert this NFA to its equivalent DFA. As before, the first step is to write the state transition table of the NFA. So we will begin with writing the state transition table for this NFA. So the NFA has three states A, B and C, A being the initial state. On state A with input 0, the NFA goes to state B. On state A, there is no transition for input 1. On state B, there is no transition for input 0, but on input 1, the NFA goes to state C. On state C with input 0, the NFA remains in state C, and on input 1 also, the NFA remains in state C. So this is the state transition table of this NFA. In the next step, we write the state transition table of the corresponding DFA. So this is the state transition table of the NFA. Let us convert it to the state transition table of the corresponding DFA. So to do that, once again, we start from the same initial state because the NFA and the DFA will have the same initial state. So we start from state A. On state A with input 0, the NFA went to state B, so the DFA can go to the same state B. But on state A with input 1, there is no transition in the NFA. So what should be the corresponding transition in the DFA? In such cases, we take the DFA to a trap state, and trap states are commonly denoted as phi. A trap state is a state from which the DFA can never go out. So once it enters the trap state phi, it will always remain there. Okay, so the next state in our DFA is B. Now in state B, again, if you see with input 0, there is no transition in the NFA. So corresponding DFA will go to our trap state phi. On state B with input 1, the NFA goes to state C. Hence the corresponding DFA will also go to state C. So next is state C. On state C, the NFA always remains in state C irrespective of the input. So the DFA will do the same thing. On input 0, it will remain in state C as well as in input 1. Finally, we have to consider state phi, which is again pretty simple. On state phi, the DFA remains in state phi irrespective of the input. Whether it is 0 or 1, the DFA will always remain in that state because it's a trap state. It will never come out of that state. So this is the state transition table of the corresponding DFA. In the next step, we draw the state transition diagram of the corresponding DFA. So we start from the initial state A. On state A, if we receive input 0, we go to state B. And on state A, if we receive input 1, we go to the trap state phi. Since phi is a trap state, so once we enter this state, we will always remain in this state. So there will be a loop on phi with input 0 or with input 1. Now on state B with input 0, we take the system to state phi, and with input 1, it goes to state C. Remember, state C was a final state in the NFA, so it will be a final state in the corresponding DFA. Now on state C, if we receive input 0 or input 1, we will remain in that state. So this is the design of the DFA, which is equivalent to this NFA. In other words, we have converted this NFA to its corresponding DFA. So in this class, we discussed about a problem on NFA to DFA conversion. In our next class, we will continue this and do some more practice on NFA to DFA conversions. Thank you.